Hi, welcome back to our lecture on a practical guide to quantitative finance interview. Today we are going to talk about expectation, variance, and covariances. So let's go through all the definitions. We have the expected value, which is just EX. If we have a random variable X, it is a random variable, okay? And then we also have the variance. X is going to be the second moment of X minus the square of the first moment, which is just the expectation, okay? And it actually measures the diffusion from mean, which is also the expected value. And we also have the covariance, which we are just trying to replace this EX here by X and Y. So if you can see, if we replace Y with X, then this one reduced to variance X, right? So variance X is basically just covariance X, okay? And then correlation is just a way to standardize the covariance because it is going to divide the covariance by the standard deviation of X and Y. And if they are independent, these two random variables are independent, then the covariance is going to be 0, and thus the correlation is also 0. But this is one direction, okay? So if X independent of Y, then we can have covariance equal to 0 and correlation equal to 0. But this direction is wrong, okay? So I'm going to give you an example here. So for example, if X follows a uniform -1 to 1, which this distribution we have just introduced during our last lecture, and then we define Y as X squared, then of course, X is dependent with Y, right? But are they uncorrelated? Yes, because the covariance is going to be EXY minus EX EY. And we are going to have this is 0, this is 0, and this is 0, and it's equals to 0. So you can see here, the definition of dependent is related to the random variable's characteristic and property. But for covariance and correlation, they are simple numerical calculation, right? You can just intentionally make up some numbers to make it equal to 0, while those two random variables are still dependent with each other. Okay, and there are some general rules of variance and covariance. For example, if there are two parameters before X and Y, then we can basically simply move them out. So, but if it is variance AX, then it is going to be what? A squared variance X, because this is going to be covariance AX, okay? And the variance can also be divided into if there are n variables, then it can be the variance of each of these variables and plus their covariance between each of them, okay? And we also have the conditional expectation and variance. Basically, we just need to replace the probability part in the expectation formula with the conditional one, okay? And the function remains the same. There is no change about that. And last but not least is the law of total expectation, which is derived from what? The law of total probability, right? Because you can regard the expectation as another kind of probability, so it's basically the same. We just need to consider all the conditions and then sum the multiplication of each case. So now let's start our today's questions. So the first question is called connecting noodles. We have 100 noodles in your soup bowl and being blindfolded. You are told to take 2 ends of some noodles in your bowl and connect them. You continue until there are no free ends. The number of loops formed by the noodles this way is stochastic, which is totally random, and calculate the expected number of circles. So again, when we have a big number in our question, what are we going to do in the first place? We start from the simple case, right? Let's suppose we only have n equal to 2. We only have 2 noodles in my soup bowl. Then the expected number of circles is what? Yeah, we have 1/2 probability to have one circle because we are just connecting the two ends, and we also have oh, sorry. So let's start with the most simple case, okay? So the most simple case is n equal to 1. Then of course there is only one way to do that. And how about n equal to 2? For n equal to 2, we are going to have 4 ends, right? We are going to have 4 ends. So let's write the ends here. This has 2 ends, so there is only one combination. So the total weight is 4, 2, which this is 6, okay? And among them, 2 combination, which means if I picked one end of one noodle and another end from another noodle, then no, and I pick another end of the same noodle, then they are going to form a circle. And for the other case, then for the other 4 choices, if I pick one end from one noodle and another end from the other noodle, then they are going to form a big circle, right? They are going to combine 2 noodles into one. So this case is going to give us 1 plus expectation of F1, right? And plus 4/2 multiplied by expectation of F1, right? They're going to have 1 noodle. And this is going to be 1/3 plus 1, because this is 1 here, and we're going to have 3/2 here, and this is 1/3, 1 plus 1. Okay. And how about n equal to 3? N equal to 3, in total, there are 6/2 choices. And among them, again, there are 3 choices. If I pick 2 ends of the same noodle, they are going to reduce the case to 1 plus E F2, right? And plus what? Plus there are another 12 cases over 6/2. They are going to be F2 because 2 lines will be combined into one noodle and it reduced to the case of F2. So, and by calculating that, we can find this is actually 1/5 plus 1/3 plus 1. So by induction, we can get what? When n equal to n, the expectation of Fn is going to be 1 plus 1/3 plus 1/5 plus all the way to, this is 3, which is 2n minus 1, right? And plus 2n minus 1/1. And well, and we just take n equal to 100 into this formula, and we can get our answer. Okay. So for the next question is frequently seen of corporate finance for lectures. So you just bought 1 share of stock A and want to hedge it by stock B. This is classic pair trade, right? Pair trade is quite classic. It's basically one of the foundations of the statistical arbitrage. We long one asset and short another to hedge certain ratios or to make it market neutral. And how many shares of B should you show to minimize the variance of the hedge position? So let's define this stock A as RA and the stock B as RB. Okay, and now let's denote this ratio as let's call it H. Then the ratio is H, and then the whole portfolio is what? RA minus H RB, right? This is going to be our return. And then the variance of RA minus HRB according to our formulas before, right? The formulas here. This is going to be variance this is going to be sigma A squared plus H squared sigma B squared minus 2H covariance RA and RB. And we also know that this one can be converted to what? The correlation multiplied by the standard deviation of A and standard deviation of B, right? So this is going to be sigma A squared plus H squared sigma B squared minus 2 rho H sigma A sigma B. And now we are going to minimize the ratio. So minimize this part. So we need to take a derivative, right? We need to pick a certain ratio. So we take the derivative of this thing called on H. And this is canceled out. This is going to be 2 sigma B squared H. And this is going to be 2 rho sigma A sigma B. And we let this formula to be equal to 0. We're going to have H equal to rho sigma A divided by sigma B. And this is going to be the optimized hedge ratio. Okay. And please remember that because it is actually quite classical solution while you are trying to do a pair trading, right? You just need to calculate the variance of two assets and also their correlation, and then put the ratio together. Okay. So now let's come to the third question, the dice game. So we see our old friend again. Suppose you roll a dice. For each roll, you are paid the face value. And if the roll gives 4, 5, or 6, you can roll a dice again. Once you get 1, 2, or 3, the game stops. What is the expected payoff of this game? So let's first define the expected payoff. The expected payoff is, let's call it just EX, okay? And then the EX is going to be what? So we have 3/6, which is 1/2 chances to get 1, 2, 3, right? And in that case, it is just expectation of X conditional on get 1, 2, 3, and plus what? 3/6 and multiplied by expected of X, get 4, 5, 6. This is derived according to what? According to the law of total expectation here, okay? This one. So this one is simple. When we get 1, 2, 3, since we have all equal probability 1/6 to get either 1 or 2 or 3. So this is basically 1/2 multiplied by 2, right? So the average is just 2. And plus what? Plus this is 1/2. And if I get 4, 5, or 6, I can roll the dice again, which means I can continue the game. So, but at the same time, I already get the expected value from 4, 5, or 6, which is 5, right? And plus the EX, because we can play the game again. So we have what? Let's denote this as Y, okay? So we have Y equal to 1, equal to 7/2 plus 1/2Y. So we can get Y equal to 7. And this is our expected return, which is EX, okay? Okay, so next question, the card game. Still another our old friend. What is the expected number of cards that need to be turned over in a regular 52 card deck in order to see the first ace? It seems a quite complex problem, but I'm going to first solve this one in a quite elegant way and then trying to generalize the case, okay? So we already know that there are 4 aces, right? And there are 48 other cards. Let's introduce a new principle here. So we are going to define some dummy variables. Dummy variables are quite helpful when solving this kind of counting problems related with expectations. So let's define a dummy variable xi. For dummy variable, it can either be 1 or 0, right? The value can only be chosen within that, okay? So this is going to be 1 if the card die is turned before 4 aces, okay? And otherwise it will be 0. And then the total number of the cards that need to be turned in order to be seen for the first ace is what? Is x plus 1, because this is the number where the first ace is turned. So it need to be counted as 1 time, okay? And plus what? Plus the sum of I equal to 1, 48 xi, right? Because this is, in any other case that do not satisfy our condition, it is going to be 0. So the sum basically represents the total expected number. So it's actually a tricky way to converge probability into expected number, okay? For discrete distribution. So how can we solve this one, right? How can we solve this one? Because we are now what we want to get is what? Expected x equal to 1 plus sum of 48, right? Expected xi. And we know that all these 48 xi's are similar, right? They can be replaceable with each other. But the thing is that if I draw 4a here, there are 4a, right? And there are 5 positions that a car, except from A, can be drawn. So if we need to satisfy our condition, that need to be drawn here so that it is before all 4 aces, right? And now the question becomes what? Right? Because for each drawing, the car can have equal probability to fall into here, 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 and here, right? So expected xi is going to be what? It's going to be 1 over 5 because it only have 1 over 5 chances to fall here before all 4 aces. So this one becomes what? This one becomes 1 plus 48 multiplied by 1 over 5, which equal to 10.6. Okay, but this is just a simple case. We can generalize that there are m ordinary cards and n special cards, right? And the expected position of the first special card is what? It is going to be 1 plus n plus 1, okay? Which means if we have more special cards, then we need less time, less cards to see the first ace. That is quite intuitive. And if we have more ordinary cards, then it takes us more time to see that. And this can be more general. For example, you know, at the end of the year, there will be a lot of celebrations in the companies, right? They're going to have some annual meetings or some gala shows, and there are going to be some kind of lucky draw activities where basically we only have 1 first prize, right? And maybe 100 unlucky pick. Okay. So assume the game is fair, where the first prize is not going to has been set to some certain people. For example, your boss or your boss is Xiaosan, right? Anyway, it's just a joke. Then the ratio is going to be what? The expected number, the expected position of this first draw card is going to be 1 plus 101. Sorry. This is 1 plus 1, right? And this is going to be 100. So it is going to be 51. So basically, if you are a statistician, you want yourself to be the 51st people come to the stage and you can get the prize. But if you are a statistician, you should also know that the probability of getting the prize at any sequence is equal, okay? It's equal. But it is just conditional on that all other people before you didn't get the first prize, then you should be the 51st person, okay? So still, but the probability of winning is still equal, okay? No matter if you are the first one on the stage or the last one, as long as it's a fair game, okay? I just want to make sure you understand that. So now next question is a difficult one, a coupon collection. So let's first read the question. So there are n distinct types of coupons in cereal boxes. for Americans, they like to eat cereal as for breakfast, and there are a lot of cereals designed for children, and they sometimes put little coupons or little toys in that. So for each type, independent of previous selections, they are equally likely to be in a box. So there are two parts of the question. Let's first see the first one part. If a child wants to collect a complete set of coupons with at least one of each type, how many coupons or boxes on average are needed to make such a complete set? Again, so for this kind of discrete case and related with the counting things, we want what? We want to define a dummy variable, but we want to find a good way to define it, okay? So in this case, because we want to collect a complete set of coupons with at least one of each type, then I can define an xi. So let's first find the pathway, okay? Xi equal to 1. It is going to be 1. If after I minus 1 distinct types, the next draw is not a new one. Okay? Then we can have something, and this is just otherwise. And we can have some kind of y equal to sum of xi plus 1 plus blah, 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 blah. And I just denote it with y. And this total sum is going to be what? This is just the number of additional coupons needed to have the i's new type. Okay? And then the total coupon needed to get n is just what? It's just the sum of I equal to 1 to n yi, right? And we know that actually yi follows what? Yi follows a geometrical distribution with winning rate what? The winning rate is going to be less according to the types we already shown, right? So at the very beginning, it is just a y, right? For the first row, it must be a new type. But then later, it is going to be 1 minus what? I minus 1 over n, right? Because there are already I minus 1 types shown within the total n types. So the probability to have one new type is just 1 minus I minus 1 over n. So according to the definition of geometric distribution, the mean is what? The mean is just the expected number we need, which is n over n minus I plus 1, because this one is equal to n minus I plus 1 over n, and then it's just the inverse of that, okay? So this is going to be sum of n over n minus I plus 1, which is going to be n, and within it is 1 over n plus 1 over n minus 1 plus all the way to 1 over 1, okay? And then we solve this part. So how about the B part? If the child has collected n coupons, what is the expected number of distinct coupon types? Again, we want to define a dummy variable. So this time the xi, let's equal to 1. So if at least one coupon of i's type is in the set, and 0, at least 1, okay? As long as we have 1 or 2, no matter 1 or 2, it is going to be denoted as 1. And 0 is otherwise. So for this, so after we define that, the expected number of distinct coupon types is just y equal to what? Sum of all xi, right? From I equal to 1 to n, right? Because if there is already one type, then it is going to be 1, as long as at least one coupon is here. Because there are in total n types, okay? So for the first type, so xi means for the first type, if there is at least 1 in the set. And for the second, it's for the second set, for the second type. And then for each collected coupon, the probability that it is not the ith coupon type is 1. So there are in total n types, and we are calculating just the one type of that, the ith type, right? So the probability of this coupon is not ith type, is n minus 1 n. And then if none of the coupons is the ith type within the n coupons, it is going to be n minus 1 plus n over n, right? And the 1 minus this is equal to what? Is equal to probability I equal to 1, right? So this is the probability that at least one coupon of ith type exists in these n jaws, okay, in the n set. And we are going to have this expectation of y is just n multiplied by expectation of xi, sorry, xi here. And this is going to be n expectation xi equal to 1 multiplied by probability xi, which is here, plus what? Plus expectation of xi equal to, oh, sorry, so this is 1, right? Plus 0 multiplied by the probability of xi equal to 0, and this is canceled out. So we only have this part left, and this is going to be n1 minus n minus 1 over n. And we solve the question. Okay, so for this question, I want you to really think about it. I think the difficulty all lies in how to define a good dummy variable to help you to convert the question into a counting one, into a simple counting question, right? And now the last question is joint default probability. So, oh, I see the picture is not here. Then I'm going to write down the question here. So if there is 50% probability that a bond A will default, and 30% probability bond B will default. What is the range of the probability that at least one bond defaults? And what is the range of A and B's correlation? Sure, okay. So there is a 50% that A is going to default and 30% that B is going to default. What is the range of probability that at least one default, and what's the range of A and B's probability? So this is a kind of range problem. So we need to have some scenario discussion about some extreme cases, the maximum and the minimum and things like that. So let's start with the maximum. Of course, if A and B are independent, of course, if like when A default, let's write it down here. If when A defaults, B never default, and when B defaults, A never defaults. In that case, the range of probability that at least one default is what? This probability is going to be 50% plus 30%, which is 80%, right? And how about this is the max case, okay? How about the minimum case? Which means that whenever A defaults, this code stand. It is because the sum of these two probabilities is less than one. Okay, it is still less than one. Okay, by the way, whenever A defaults, B also defaults. Because probability A is larger than probability B. Okay, so we do not say that when B default, A also default. It's not necessary. And this probability is just what? 50%, right? And now we already solved the first part of the question. Then what is the range of A and B's correlation? So let's first write down the correlation, right? The correlation probability A or B default can be converted into what? Can be converted into expected of A default plus expected of B default minus expectation of A and B, right? So what is this I here? Let's denote I here. It's a random variable. So this I is the dummy variable. Again, a dummy variable. Okay, IA, IB, dummy variable equals 1 if A default. Okay, let's just write it as IA. So IA and equal to 0 if A not. Okay. And this IA follows a what? Follows a Bernoulli distribution with the probability for A, it is 50%, right? 0.5. And IB follows what? Again, a Bernoulli 0.3. Oh, sorry, there is no N here. This is Noulli. Okay. Noulli. And we know the expected value for Bernoulli distribution is going to be 0.5 multiplied by 1 minus 0.5, which is 0.25. And the expectation of IB, which is 0.3 multiplied by 1 minus 0.3, which is 0.21, right? Sorry, this is a variance. So this is a variance. This is a variance. And the expected IA is just 0.5, and expected value of IB is just 0.3. So we just need to put into the formula. This is IA and IB, right? So this is by A or B is equal to probability A plus probability B minus probability A intersect with B, right? According to our first lecture when we're talking about the probability sets, right? So it will be the same for the expectation. And for this part, then we calculate that this is 0.5, this is 0.3, and this one is going to be what? It is equal to expectation of IA multiplied by expectation of IB minus what? Minus the covariance IA, IB. And this part is going to be equal to what? Correlation AB, which is what we want, right? The range of A and B's correlation, multiplied by the square root of variance IA, variance IB. And let's put them all together. This is going to be 0.8 minus 0.5 multiplied by 0.3 minus rho AB, and this is going to be square root 0.25 and 0.21. And this is going to be 0.65 minus square root 0.21 over 2 multiplied by rho AB, right? And we know this one is within the range of 0.5 to 0.8. And we can get that the correlation range is within negative square root 3 over 7, and this is positive 3 over 7. So why I start the question with the discussion of the probability 50% and 80%, why not I just list out this formula in the very first beginning? Because if I just list out this formula, then we may think the rho AB's range is within what? Is within 0 to 1, right? But it is not the case, because by the probability of A default and B default, the correlation has already been set into a more minor and shrinked range, not 0 and 2, 1 anymore, okay? It is less than that. And we can also see that if we solve the question from another side, and that's what I recommend to you. Let's first discuss all the trinomials in this question. Do not start with 0 and 1 in the very first beginning of the correlation, unless there is no extra information in this question, okay? And that is going to be all for today. So the next lecture, we are going to talk about the order statistic. So see you next time. Thank you for watching. And do not forget to subscribe and 一键三连, okay?